Hey everybody. So today we are talking about bond energies. And pretty much what we're going to do is we're going to figure out the enthalpy for a whole reaction, just given the energy in between bonds. But first, let's talk about some conceptual stuff first. What we have here in this table is just all the energy that is stored in certain types of bonds. Some are stronger than others, and some are pretty weak. So let's talk about what makes bond energies stronger. Here we have some single bonds, and you can see we have 436, 431, 567. We got some in the hundreds here that are pretty low. Kind of same here with all these single bonds. But then when we hit these double bonds, we start to see the energies increase. And you could probably take a guess as to why the energy increases in the double bond. And the thing is that there's just twice as many bonds, right? A bond between H and H with a single bond isn't going to release as much energy as a oxygen with a double bond. Okay, so that's just it. As we increase in bonds, we start to get stronger energy in between those atoms, right? Same with this N to N triple bond. It's a really high energy here. So it's just good to know that the higher up we get in bonds, the stronger they are. Another good thing to know is that single bonds are the weakest and have the least amount of energy, but they are the longest. Double bonds are stronger, but they end up being shorter. And then nitrogen bonds are the strongest, but they are really short. Okay, so the stronger we get, the shorter the bonds get. Okay, nitrogen has 3, it's the strongest, has the most energy. H to H single bonds are the weakest, and that's because they're just single bonds, but they're also the longest. So let's go ahead and let's get rid of these. And let's talk about kind of what's happening with just these single bonds right now and why some are stronger than others. If you notice here, we got some pretty strong ones going on, but really this hydrogen to hydrogen is oddly strong as well. Why is hydrogen bond so strong? If you know the Hindenburg, it created a big explosion, released a bunch of energy, and this goes back to our Coulomb's law, right? Coulomb's law, which we talked about briefly in that Pogel, is just the charge in between atoms, or the strength of the atoms, is going to be based on their charges, which is what these Q stand for, and then the distance away from one another. This K is just a constant, but R is the distance they are away from one another. Well, with hydrogen, okay, this is a covalent bond. Hydrogens are just really small. They're really tiny atoms, so they could be really close to one another. Okay, they're really, really small, so they could go ahead and be really, really close. So if this R is super small, that charge between them is going to be really, really strong. So it takes, when they get broken, a lot of energy gets released. Okay, even more than a HCl bond. And then you could also notice, why is this HF so strong? That's just because it's a ionic bond. Hydrogen's going to give up an electron to fluorine, so fluorine becomes negative, hydrogen becomes positive, and then they get attracted really well, and that's a really strong bond where a lot of heat is released. Okay, you kind of notice that trend as well in OH. You kind of see this nice little increase in energy. All right. Fluorine, not so much. They're both nonpolar. They're not going to attract electrons to one another a certain way. They're going to not be so strong of a bond. Okay, so be aware of that. Be aware that size of an atom matters, and also the differences in electronegativity matter based on how much energy they release. That's just a good conceptual thing to know of. Also, it's good to talk about, or just revisit, I should say, Coulomb's law, right? The stronger the charges and the farther, or the smaller the distance, the stronger the charge is going to be between them. But that's it for our conceptual thing. Now let's talk about what we're really focused about today. So like I said, when a reaction happens, these bond energies break and they absorb. And sometimes you might absorb more energy than you release. Sometimes you might release more energy than you absorb. And the way we figure that out is that if we want to find delta H, we just take the bond energies of the reactants and subtract the bond energy of the products. Okay, so when we did heat of enthalpy, right, they'd give us the whole enthalpy for the whole compound. And then we would do products minus reactants. And most things in chemistry are products minus reactants. This is the only thing you'll see in AP chemistry that is reactants minus products. The only thing. Everything else in chemistry, and usually most sciences, is products minus reactants to find the change. In this case, it's reactants minus products. Okay, so remember that. Reactants minus products. So how are we going to use this formula to help us? Well, let's do an example. Say I have hydrogen gas and fluorine gas. They're going to react with one another to form two hydrofluoric acid or hydrogen fluoride. What we do is we draw the Lewis structures for each of these guys. The lone pairs don't really matter at this point because we're just focused on bonds. So I'm just going to draw the Lewis structures for both of these. And what we're going to do is we're going to go ahead and use the bonds and all these Lewis structures and these average bond energies to help us figure out the delta H of the whole reaction. Okay? And we do that by using this equation right here. So we're going to take the bond energy of our reactants. H to H is 436. F to F is 155. Okay, reactants are done. Now let's subtract our products, which we have two H to F bonds, which are going to be 567. All right, we go ahead and we do all that. We plug it into our calculator, and now our delta H should be something like negative 543 kilojoules per mole. So before we were using, they'd sometimes just give us the whole enthalpy of H2, the whole enthalpy of F2, and the whole enthalpy of HF, and we would do products minus reactants. But in this case, we'll be using bond energies because that's what they give us. So we'll be doing reactants minus products to get our enthalpy. Okay, and that's what we are doing today. So let's go ahead and let's do another one real quick. Let's stay right here. Let's do, once again, something a little simple, and then we'll go a little bit more difficult. H to H. So hydrogen gas. I want to erase that. Chlorine gas. And it's going to make two HCl's. Okay, so let's go ahead and let's look at our bond energies. Remember, it's reactants minus products for this one. The only one that you'll see where it's reactants minus products. H to H is 436. Reactants minus products. Our other reactant is Cl to Cl, which is 242. Subtract our products, HCl, which is 431, but we got two of them. So we do 2 times 431. And I'm going to plug this into my calculator. You should get negative 184 kilojoules per mole. Okay, heat was released. This is exothermic. These are both exothermic, right? So that is the simplest bond energy problem you will encounter. Let's go ahead and let's do one more slightly difficult example. Say we have hydrogen gas plus CO2, and it forms H2O and CO. Okay, here we got to make sure our Lewis structures are correct. All right, we got to make sure that our formal charges are right so that we got the right Lewis structure going on for us. Hydrogen is pretty easy. It's just a single bond. CO2 is one of those ones where it is a double bond to each of those oxygen. Okay, every one of these has a formal charge of 0. H2O, we've seen that enough times to have that down formal charge wise. And then carbon monoxide ends up being a triple bond. Carbon has a -1 formal charge. Oxygen has a +1 formal charge. They end up being 0, okay, when you add them together. There's no way to get carbon and oxygen both 0 to 0. Okay, if I did a double bond, I'd have a -1 carbon and a 0 oxygen, and that wouldn't fly. So let's go ahead now that we got our Lewis structures and find our bond energies. H to H is familiar, 436. C to O. Remember, you got to count all these double bonds, right? So there are 2 C to O double bonds, which ends up being 799. So don't forget to include all the bonds, especially when we get into like crazy compounds or molecules like this one, right? You have to count all 3 C to H bonds and that single C to Cl bond, okay? But let's get that out of here because I was just giving an example. And let's go back to our original problem. So there are all my reactants. Now let's subtract all the products. H to O, there's 2 of those guys. 1, 2. H to O is 463. And then last but not least, our C to O triple bond, which is 1072. So now that we got that figured out, let's go ahead and plug it into the calculator. And I ended up with a enthalpy or delta H of 36. So this one's positive. So we will end up with an endothermic reaction here. This is actually going to absorb energy more than it releases, okay? So 36 kilojoules per mole. So that is bond energies. Remember, it's reactants minus products. Make sure you're including all the bonds in these compounds, okay? Don't just do one C to O double bond because there's 2 of them. Make sure that you are using the correct bonds. Make sure that you're saying if these exothermic or endothermic when asked. And that is it, guys. Have yourselves a good day.